Hi everyone, we will start in 1 minute. Good morning. So good morning everyone. One more time. Let's start our lecture. And today we'll switch from classic methods for the processing of sequential data to neural networks. We'll start with general overview. Why do we need neural networks? And this may be pioneering application of this particular method, machine translation. And then we'll introduce historically first successful model for the processing of sequential data, recurrent neural networks. You'll be able to see exact formulas and some tricks, some modifications that are required to produce a reliable result in the end, and some quite popular modification of RNN. Basically, everyone is trying to do something like this. In particular, I am talking about LSTM and GRU modifications. Then in the end, we'll discuss, can we achieve better within the framework of a single recurrent block that takes as input something at each step, and can we success in our quest for a better recurrent neural networks, or do we have some limitations? And actually, we should do something different to improve the quality of the model. So let's start from some short reminder of what we did 2 lectures ago. We say, okay, if we want to apply some kind of machine learning for our data, we will require some features. As we have this sequential data, then we have some maybe related data to this particular sequential nature and particular features for this type of service. And so we say that we generate variables that are past values of our initial time series we want to predict. We also can focus on something else. 1 minute, please. I will add my tablet to and I will be able to conduct the lecture more successfully. Okay, so what I'm trying to say is that, okay, we have some time series, okay, x t minus 3, x t minus 1, t minus 0, and so on. And we say, okay, to predict this guy, we collect the past observations of this particular x, form a list of features, add something different, maybe some other features here, and have like these features as input. And this is what we predict as output. So we have a regression problem, and we have this common tabular data. So we can apply practically any approach to train this model. For example, we can try to use gradient boosting, for example, and it will give us pretty fine model to deal with. So what's the limitation of this approach? The limitation is that we need some features that like as input. And in some cases, it's quite different, a difficult problem to generate such features because we should construct some representations in the case of structural data. And we have a lot of structural data out there, starting with audio data. So we want some speech processing, and we have a model like speech to text, for example, or we have a sound and we want to classify sounds that belong to different birds. Also, we can switch to NLP domain, and our input is now again something structured but different. Right now, it is a text, a sequence of words in some language, and we want to either solve classification problem or regression problem. Guys, please turn off your microphone if you don't want to ask any questions. Also, we can say that sometimes you want to ask an output, some other sequence, which is also a structured sequential data. Also, we can imagine that we have a video, and again, for a video, we want to identify some action related to these videos. For example, you can identify that, okay, someone is running here, or someone is taking off from a chair to another video, and so on. And in all those cases, it's kind of natural to think that we need a neural network, for example, a convolutional neural network, or maybe something more interesting to succeed, because we need representations in the middle layer here that we will be able to produce a required input. So definitely we need some neural networks. And also let's convince you with one and with other toy example, but pretty strong one when we're trying to deal with this problem in other ways. So we are thinking about something quite simple. We are thinking about predicting a next word in a sequence. We can say that, for example, we can want to model the distribution of a new word given our previous words, for example. Okay, maybe it would be more common to think about it like this, or whatever model we apply, the goal is the same. We want to predict the next word given all the past information. In this case, we can try to say we don't want to have a lot of data, a lot of inputs, and basically we want to have a discrete single size input. And in this case, we kind of use only the last word to predict the next word, because we don't want to store all this information here. So basically we train, instead of this full model here, we switch to another problem, basically x given y. Okay, what's a good news is that for this model we can train something very simple, and with high probability we will have enough data to approximate this dependence quite good. But what's the problem? The problem is, I think you agree with me, that if we are talking about predicting next word, it's pretty important to take into account all the context we have in our data. So we should not only look here, but look here and here and here to be able to make more reliable prediction. And in this example out there, you can see that it's crucial to see what's in the past to predict the future. And sometimes we should dive past quite deep to get to friends from something that they speak fluent. So quite possible it's like French, but to know this answer to the question, what's the next word, we should look at the previous sentence. So we need something more interesting, but one more concept as a slide is a representation, what we can construct using this simple model. In this case, we can say, okay, we have like all our dictionary of words, like 200,000 of words. And so let's introduce a feature vector of size g that equal to 200 thousands. And we say that for each word, we have an encoding or representation that has one simple one at the place related to the particular word to this word. Just for example, add zeros at all other places. Okay, it's one-to-one representation. It's kind of a lot of like interchange between the representation and the initial word. Bad thing here is that right now we have very sparse representation, a lot of zeros, hard to store, hard to build reliable models. So we can try to improve both the representation we have to predict the output and also take into account that we have these long-term dependencies that we want to work with. So we say, okay, let's have a representation of a sentence as a bag of words. And in this case, we put not only zeros and ones, but put some numbers. And the number is the number of occurrences of a particular word in a sentence. So we have like this more common feature vector. It's still extremely sparse because we have a lot of words that like are not presented in this sentence. So most of these representations, the components of this representation will be zero, but still we will have rich information and we will have a chance to predict the next word with higher accuracy. But again, we are missing some parts of this representation of this data. We say that order is also important. Okay, you agree with me, especially if you're talking about words, but for other problems too. We are usually more interested in what's going on right before the event. We're not interested in something that's in a long past. When we're thinking about some periodicity data, what we talked about during the previous lecture, we also say that there is some more important parts in our time series because it corresponds to some period past here. But if we are thinking about this bag of words or something similar like GFIDA features, we are dropping this information. And so there is another example that illustrates this the wrong approach if we want to construct something general. We can say, okay, we have two sentences. The words exactly the same for the top one and for the bottom one. So the food was good, not bad at all, and the food was bad, not good at all. That's the same sentence with two words interchanged, but the meaning is different. So if you're talking about text, we again have this problem. We want to take into account the order when we model our data. So if we want to list all problems, all design criteria for our model to be successful, for modeling of complex time series or sequential data, we would think about something that, in the first place, can handle variable length sequences, and this is what this model will do. Also, we have three other criteria that are crucial for the success of our model. We want long-term memory. We want to take into account something from the past, but also we want to have some balance. If we have too much emphasis on the past, or we store too much information, then we may be missing something that can be crucial in some cases. Also, we say that it's important to take into account that we have some particular orders of words, events, observations, and if we put everything in a big hill of words or anything else, then maybe we're missing something very important, missing the structure we want to use when making accurate predictions. And also, last point, but not the least, is that in many cases we will need some natural preprocessing of the data, because if we are not doing this kind of things, that we miss something very important. And when we are talking about NLP, for example, there is a large part of each project on how to prepare the data, lemmatization, all the stuff. And so we often want to deal with this kind of things when we are trying to construct a more complex model. We'll say, okay, we will have the solution in a moment, quite good one, recurrent neural networks, but we'll talk about it a bit later. When we go back to classic machine learning model based on TF-IDA features or based on bag of words, or using only previous words, then we definitely have some problems, and we don't meet all design criteria I listed as a previous slide. We don't have long-term memory, or if you have this memory, it's kind of very strange memory. We don't maintain order information here. Also, okay, it's a problem to have some preprocessing. We should put more emphasis and generate correct features. And as for all cases, when we will need good representations, but all we have is something based on engineering or expert knowledge, we have not a perfect performance. Also about the first point, we kind of, when we use this bag of words features, has this processing of variable length sequences, and we say yes, but sometimes it's not what we need actually, because you can imagine that you don't want to have one word predicted, but you want to have many words predicted. How to deal with this is classic machine learning models, not clear. We can try to have a separate model each case, like yt plus 1, yt plus 2, yt plus 3, and so on. But definitely, this is not something you expect to work from scratch in a very fast and reliable way. Contrary, we expect this model would perform quite poor, so you'll need a replacement. And we hope to find this replacement in the world of deep learning. Similar to what we have before for image processing, we say, okay, in the past we have this art of feature construction. A lot of the SIFT, HOG, GIST, and all other dangerous words here to generate features from images. And then we have these representations, and from these representations, we predict the actual output we want from our model. And this is not the way. A good, better way for computer vision and for sequential data processing is to have a deep neural network that can automatically construct representations. It's like a single concept, end-to-end, everything you need. And we hope that it will work better. Also, it utilizes a lot of things we have right now in the market and in our science of data processing, of machine learning. And so when we look at the problems listed closer to the beginning of the presentation, we see that actually for all these problems we listed, okay, even for the DNA sequence analysis, we say that we have a large data set and we have semi-structured data. And this means that we will need a right neural network to process all the data. And even a simple one, I can generate pretty surprising nice thing. For example, we can try to learn a model and generate some text, and when we are looking at even simple examples, you'll see some very interesting results. For example, we can generate texts with mathematical formulas like LaTeX. And for this LaTeX, we see that it looks quite professional. Okay, it's complete nonsense, but it looks like a real mathematical text. Also, we can try to generate everything we want. Shakespeare plays, Wikipedia articles, algebraic geometric articles, some source code, names of dinosaurs. So whatever, so we have this freedom of not trying to tailor and spend a lot of time for tailoring of the model, but try to provide something more universal end-to-end. And this is what we hope when we're trying to construct representations and in general solve our problem with neural networks. And this would be the only way in many cases. We can't solve all problems for classic machine learning case. With classic machine learning, if we have a sequential process. Yes, in some cases it's kind of useful. Even TF-IDF features in some NLP problems. Okay to use them. And when you're approaching new problem, it's worth a try to do something like this. And often if you have enough this work, better than even transformers, birds, whatever. But generally, if you want to have like, and similar thing happens in different areas when we are thinking about processing of sequential data. But like, okay, more general would be to have this representation here. And you'll see that even for a simple model, we will have quite interesting and good results. So we will continue this machine translation application example. And now I ask you to turn on your cameras, and I will take a screenshot to have this participation list. Okay, you have 1 minute to do it, and after it, I will fix it and send to ZTA. Okay, so 5 cameras on and 4 more to go. Okay, Edward at the beginning unfortunately can't complete it, but okay. So be it. 1 minute, please. I will send it and I will then go back to you. Okay, so let's continue. Thank you for turning on your camera. So it will help with the attendance. And right now we continue with another example related to machine learning and deep learning, and in particular sequential data. We are working with in this course. So like it may be one of the most interesting and applications, and one that drives whole industry of natural language processing a lot, like a cornerstone problem. And so let's see how it progresses and why do we need neural networks in this case. So you say, okay, we have 50s, and like the era before the first winter of artificial intelligence, and someone is already doing some machine translation, and the first one is translation from Russian to English, IBM 701 translator. Okay, when you look at the proposal of this project, you can see that participants were pretty inspired about what they're going to do, and they say, okay, in 5 years you'll have this general machine translation problem solved and all. But the model was pretty simple. Actually, it was a rule-based approach. We have this English-Russian dictionary to translate from English to Russian, for example. And what the model actually did, it like look at the word here. Okay, tried to find something in the dictionary, like in this case it would be doctor in Russian, and continue like predicted. We can't find it like in a regular dictionary, but perhaps we have this extended one, and we have this for infinite form, not very good one, and doctor something the dictionary for sure doesn't know, and in the end we have very strange thing that can be used as the actual speech, the actual text. Maybe in some cases it would be useful, but in many cases it's just completely garbage here. And okay, in 5 years, it was like maybe the first sign of an AI winter, because the project was closed. It was very expensive, a lot of people involved, but no significant progress because the model and the data was not mature enough. And so was it. And so let's see what's next. What was the next approach? Basically, we can say that we want to have this model of P of X given y, y is a text in one language, like text in English, for example, and X is text. We want to have text in Russian language. And basically, okay, we can try to introduce something like this, but we will need a lot of heuristics to have the model that translates in this way and that incorporates directly this particular distribution. It's too hard to achieve significant result, but it's possible. And big teams of engineers in Google and in other companies try to do something like this. It's interesting that these teams included not only like data scientists, but also a lot of linguists, because they tried to create a universal model for language, maybe even not probabilistic, but more general. What's happening in the language, but it's kind of impossible tasks because of the language is not something constant. Vice versa, it changes a lot on new words and new forms. You can observe every day, and when we read like Dickens or Pushkin or something like Shakespeare, you can notice that there is a lot of words we don't use right now, a lot of forms that we don't use right now. So we have this very hard system, a lot of people to maintain, highly qualified linguists, data scientists, all people. They like develop separate components of this whole system. Also complex generation in the end for inputs. And also this is something, okay, we have this complex system. We have to maintain this system. We have to change it sometimes. And so we have another big team. Even if you develop system at some time, it would be not very good. And also in the end, not only constant support needed. The result is not good. The quality is quite poor. Or maybe you can try to remember the results of Google Translate before deep learning revolution, before 2014. It's not very good thing. So quality basically is not that great here. So it was bad. But in 2014, they then produced a model based on autoencoders, basically of recurrent neural networks that like were incorporated into autoencoder, a neural network model that can solve this problem with high quality. And so what the basic idea here? We have these two neural networks. The first one is encoder. The second one is decoder. If we proceed our input with encoder, we have an embedding. If we proceed embedding with decoder, we have output. And as we have like a big sample of pairs of inputs and outputs, like sentence in one language, sentence in another language, we can train this model to have a reliable encoder and a decoder that together produces a reasonable output. And as we have a sequence as input and a sequence as output, we have a sequence to sequence architecture. Okay, this model is still not perfect and suffers from a lot of problems. For example, it's very hard for a neural network to understand the concept. And for example, PuppetGem, when it translates to Spanish, it was the case for Google Translate some times ago. it was actually the paper jam, not like what we expect, that something happens with our printer. Also, we have some biases learned from the training sample. I don't think it's like this is an important problem, but this is not problem for a model, it's problem for initial text. You can start change from yourself, not from your models you train on your data. The data always have some biases and model learns these biases. For example, here you can see that we have, okay, Malay language. There is no gender specification, like some article here, then some verb and true professions. Jurur Avat, a nurse, and Pengatur Sara, a programmer. And when translate this to English, it happens that we have this specific gender specified in the sentence. This is maybe a bad thing if you want to have this unbiased translator. Also, sometimes results are not what we expect. For example, when translate from Somali to English, we have this initial list of words, and we have translation to English. And as you can see, it sounds like a part of the Bible, because maybe it was the bias of the training data again. Because I suppose there is not much parallel corpus, parallel text for the pair Somali English, and like the book that is translated to all languages is the Bible, so it's translated to Somali too, and you can see that, okay, if you learn from bias data, you have biased results. Okay, it was a breakthrough in 2014 when I suppose Google published an article related to the application of a neural network of this sequence-to-sequence architecture to produce, to solve the translation for it. It was not the end, actually, and right now we see that the state of the art is different, and a lot of other approaches are developed, and also they are much more complex than what we have seen in the very beginning. So basic models is sequence-to-sequence model for the translation. It's very simple and actually doesn't require a large team to build. Right now, you can expect that there is a whole departments in large companies related to these products, and highly qualified scientists are still trying to improve this model and to fix, for example, these biases. So actual systems for motion translation are quite complex as any other software product dedicated to solve like a major problem, but also inside it we can see different architecture. This initial one, recurrent neural networks, are not the best right now. It was much better than other approaches, but right now not. Right now we can see that if we translate from English to German or from English to French, convolutional neural networks, the adaptation to this problem also can do a good job. And if you consider a transform architecture based on attention mechanism, we can do even better. So we can see this progress of the value of blue metric, and right now a variant of a transformer that we'll consider later in this course is the best one. So you can see that there is a different options for neural networks, and so let's try to select the best one, maybe discussing a bit what's also going on in translation. Right now we can see that, okay, if we invest a lot of time, we will have the performance of a human similar to the performance of a machine trained model. So for example, we have this a qubit model for machine translation from Czech to English with specific corpus. We want to translate news or stories. And in this case, we compare the quality of a translation by qubit model and by people. And so we have this also testing that's not conducted by some metrics like blue, but rather by a metric like human evaluation. We have some experts and non-experts that are trying to guess what translation is better. And what we can say, we say that qubit is definitely it definitely beats humans in some cases. For example, it's like more adequate, and mean adequacy score is higher for qubit than for humans. For fluency, we have slightly worse scores, so qubit is performing not that good. When we are talking about overall quality, we have like almost a tie actually with this 38% for reference for human translation and 41 for qubit being better according to human evaluation. So we can say, okay, we have solved this problem partially, but you can also observe the progress of machine translation systems by looking at Google Translate. Right now, okay, some of my students unfortunately can't produce as good translation as Google Translate, but yeah, if you are professional and you learned English and so on and learned another language, then you will do better than Google Translate, but you should invest like maybe at least 2 years to be as good as it. So right now we see that okay, this big challenging problem is maybe partly or not partly solved. In many applications, it's okay to use machine translation. In some, there is still some risks. For example, when it's related to some laws, we can say that we should have very precise translation, and the language, like in Constitution, is very difficult to translate. Or, for example, we have a manual for some device dedicated to saving people's lives and some harness systems. And in this case, you will need a human translator, because human is the one who takes all the responsibility and can provide accurate results in contrast to humans. When we're talking about specific models, the best one right now are transformers, and we consider them later in the course. And we can say that sometimes it's even better than humans. So, do you have any questions? If you have no questions, please write plus sign in the chat. If you have some questions, please ask them right now. Okay, thank you for the feedback. And right now we are ready to go with the second part. And the second part would be what kind of models are used for sequential data processing, in particular, what kind of neural networks models are used. We start with fully connected convolutional neural networks, and we'll see if they work or not here. And we can say, okay, we can have varying length input. So for each input, we should have some model. So this guy is some neural network model that produces some output. Because this is the only way we can go. We can't have like this specific model dedicated to specific lengths. And so we have this similar black box. This black box can of any type. It can be like for connected neural network, something different, some encoder, and so on. But you understand that this is not the case. We can't solve all problems in this way. When we are looking at our checklist for the properties that a good model should have, we see that fully connected neural network doesn't meet all of them. It sometimes, it can handle variable length sequences if you apply it straightforwardly, but it has no memory. It has no information about order, or at least very specific. Also, we say, okay, it can be an end-to-end model, but it's not the only problem we want to deal with. we can try to look at another quite successful model for the prediction, and also based on neural networks. It's called convolutional neural networks. And as you can see, okay, we have some unstructured input and some output. And the problem is, again, we have this variable length property. We can have in a different ways different types of sequences. So there is no direct application of convolutional neural network, or at least it would be strange. Later in the course, we'll provide some information of how should we deal with convolutional neural networks if you want to adapt them to sequential data processing and this is what called one-dimensional convolutional neural networks. It kind of works, and it works quite good actually in some problems, but direct application is impossible. So there's different lengths requirement, and also hard to mix features from different parts of the text make this model quite hard to apply. So again, we have this problem and we want to deal with it. So we introduce a recurrent neural network. Okay, maybe a short question. Please write, I'm just curious, if you, worked with convolutional neural networks or recurrent neural networks or whatever neural networks to deal with sequential data, please write 2 pluses in the chat so I can see who knows about this stuff, and please write minus if you don't know anything about it and you don't know mathematics behind it, no formulas. Okay, I will give you one minute to do it, and maybe some questions. Okay, thank you for your answers. I see that it's like half, and some of you have worked with this type of model, some not. So let's try to deal with it and try to introduce the basic concept because we'll meet later in the course, and also focus on some particular stuff related to it. So not only about the model, but about how to apply it for a particular problem. So let's go. We'll start with vanilla recurrent neural network that tries to overcome all those difficulties. And we'll say that it has some memory, but this memory is not very long. So the idea is to store the information from the past. We say that we have this black box here. And this black box, for example, we have this sequence to sequence one-to-one architecture, and we should produce something at each time moment. For example, we observe some sensor measurements. And we say that we want to say if it's anomaly or not at each time moment. Or we want to translate each word in a sequence. And in this case, we have output, y, we have input, and also we should somehow store the information. And in this case, we store this information into hidden or self state, it's like the current state of the model. We start with something. We proceed with a black box, this something. Also, we take into account that we have some input, and so we produce output and tries to incorporate all we have about the input at the current moment. So we have an update of this hidden state. Then we do this again for as many times as how many elements we have in our sequence. So for example, next time we have xt minus 1, we have as input this updated hidden state, we have this black box, and this black box produces another hidden state, and so on and on and on and on. And also we can train this black box to produce some output if we need it. And so we have like exactly what we expect. We have this memory stored in our model. And for example, and what's important, we don't need to train a lot of models, a separate model for each part. We can say that we have the same model for all the parameters. So if we assume that all input is numerical here, so cell is a vector, input is a vector, output is another vector or maybe a class label here, and also new hidden is a vector, then we can have it like this. So we can start with a general definition. So we have a separate function for the production of new hash and a separate function, this is f hash, and a separate function for the production of fy here. And we can say, okay, we can try different models, but basically we can say that we want to use only hidden state, for example, to produce the output, and to produce the next hidden state, we use new information available at this time moment and previous history stored in a hidden space. And so you can try to use some particular formulas for it. For example, we can have hyperbolic tangents for our new hash. So we have some linear transformation of x, linear transformation of hash, some bias, and nonlinearity, because we like nonlinearities. Without them, neural networks are pretty hard to remember anything. And for t with a hedge, we can use, for example, softmax function, again a linear function of hash plus some bias. As you can see, we have these parameters here, and we can produce in quite simple way the output of our neural network, new hidden state and new output if we need it. We also see, okay, it's not we see, this is actually what happens. We actually don't need to have separate parameters at each time moment. We assume that each time moment we have the same parameter here. So if we have this new time step, new xt plus 1, and want to produce ht plus 1, we just apply the same parameters here and write correct indexes to have the output. So to produce ht plus 1, we have a hyperbolic tangents of the sum of v times xt plus 1 plus w times ht plus the bias vector or scalar. So from these simple blocks, we construct the whole sequence process, and we don't care about the length. So, okay, maybe it's like a better illustration on what's going on. We just apply the same block. If we can learn these parameters, we are happy, and we just apply it until the end of our sequence. So we handle various length sequences. Also, we store history here. And if we store history, we kind of look at the past, and our model has memory. Also, definitely we process the data in a particular order. So we maintain order information. And also we have this end-to-end model that does not require much natural preprocessing. And so we have everything, almost everything we need. Actually, we have this memory, yeah, but long-term memory somehow does not learn here well. Maybe the reason is that we have very long sequences, and to be able to learn how to get information from the very past, we should learn our model a lot, and we don't have resources to do this. And so we should try to use something more complicated to be able to deal with this difficulty, or maybe apply some engineering tricks. But actually, I would like to say that sometimes vanilla RNN also can be useful, especially if you're not talking about large data and natural language processing. It's still kind of useful. So you can see that still there is some room for older methods and for very basic methods. If you use TF-IDF, it's also in many programs, it serves quite good. If you look at RNN without any additional modification, it's still we have something good, sometimes good results. And if we look at, for example, prediction of the default also based on transactions data, maybe it can be the case you shouldn't opt for transformers, or even for LSTM. It's enough to have RNN because it's simple and it can work like a charm for some problems. Also note that as long as we introduced this model, we able to solve a lot of problems. Not only like in terms of what kind of application we have, but also in terms of what we want, what's the structure of our output. If we have no recurrent structure, we have something like this. And this is what we typically don't want to do with sequential data. Instead, we would try to solve something different. The first problem is a sequence to one, a sequence to a single output. If we have a sequence, and for example, we want to have, like, we have a review of a movie, a sequence of words, and we want to produce how many like stars a user will give to this particular movie. 3 or 5 or 4 here. So the review corresponds to a single output. Okay, we can think about something completely different. About a sequence to sequence. In this case, number of outputs can be similar to the number of inputs. For example, if we predict anomalies at each time moment. But also sometimes we need to define a sequence to sequence problem in a different way. For example, if we are looking at machine translation, we need this separate encoder and decoder part, because sometimes you need to change the order of words. But even if it's not the case, the length of the sentence in an initial language and of the sentence in a new language is completely different, can be very different. So we should use it like this. A decoder, an encoder, and like this general problem statement. Maybe you can imagine something different, but mainly this main problems we have. And also you can see that we can kind of solve it. Yeah, solve it with what we already have, with this recurrent neural network. We can say that we just need this single block here and here and here. And for example, if we try to solve a sequence-to-sequence problem, we have this RNN block here to store the hidden space. Here we have a representation of initial sequence, a hidden state at the last time moment gx. Then we can try to apply a separate block to produce an output. And if we have a training sample, we can compare it to the true guys and update the parameters of this blue block that corresponds to a decoder and green blocks that correspond to encoders. So be it. So we see that as long as we introduce correct model, correct architecture of our neural network, we can formulate almost any problem of the processing of sequence data as a problem for our neural network, and we do it in a differentiable manner. Our loss function will be differentiable, and so we will be able to learn this model. So this is the basic thing, and now let's look into some details. Again, do you have any questions? If you don't have questions, please write plus sign. If no, please ask a question. Also, it would be good maybe if you if you can share on have you tried vanilla RNNs in your life and what do you think of them in the chat. If you tried and you are successful, you can turn on the microphone and tell a couple of words. I already told that I tried to do this. And the RNNs were pretty strong in some applications. So let's go on and see what else we can do on recurrent neural networks. Okay, let's start with forward propagation. As we have these formulas inside each block, we can easily produce output we want. We can say that we have a single output at each time moment, or single output only at the last moment. And we can say that in this case, we maybe have a separate full connected neural network to produce output here. But again, the general structure is pretty straightforward, and we can produce output by RNN in very reasonable way. So the parameters is what we want to learn. So if you have the parameters, if you have the model backpropagation is easy, and information flows and so on. And also, if we imagine NLP problem or any problem with categorical data, we typically have separate encoder layer that like contains embedding of a sequence. So you can say that we have a sequence here, actually, and this is our embedding of this sequence. And we learn these embeddings for each, not sequence, I'm sorry, for each word we have a separate embedding that we pass into the word. So we get rid of categorical variables and replace with something we can put to our recurrent block that has this guy to produce the output of this guy. It was like this. It does not make much difference. We have something like this as long as we have embeddings. So if you have output and if you have a training sample, we can try to compare the output to the true values. So you have true value y1 and to our prediction y1 hat. And the same thing happens for all our parts of a sequence. And as we see, we can calculate a loss function here, and typically it's differentiable loss function. So we can calculate the gradients with respect to the parameters from a neural network, and we start with backpropagation and calculation of derivatives with respect to output. Then we say that output is a function of our parameters and input, and so we can calculate the derivatives with respect to parameters and with respect to RT minus 1. And as we have this previous hidden state, we again calculate derivatives, partial derivatives for each part, and on and on and on to get the final result. So let's look at it for our part of the neural network. We have the loss function, we have the output of our RNN block, and it has the following structure. As you can see, it's a softmax function, a differentiable function of a linear function of HT of a hidden state we have right now. So actually, it's more like this, but you can imagine that we have these two steps as extrapolation here. And so we can say, okay, for each element of a sequence of the length gy, we have loss function that corresponds to a pair of initial y and y with a hat. And so if you want to calculate the derivative with respect to the parameters of this softmax block, we calculate derivatives like this in a separate way. And we can say that it's product rule for partial derivatives, and now we have derivatives for each u. And as we have these derivatives, we can run optimization and get good values of u. Okay, the situation is a bit different when we are talking about the derivative with respect to k. We don't have formulas here, and we have a formula here for ht, and we say that we have these parameters v, w, b, and we want to take the partial derivatives of our loss function with respect to this test. Okay, we can say that we start with a simple formula, but this simple formula does not work here because we have dependence on h here, and it's not that simple. Let's look in more details. We can say, okay, we have this first term, easy to calculate because it's a derivative of the loss function, like cross entropy for our prediction, and the second part. And this second part is actually, again, by a product rule, is a partial derivative of y hat with respect to ht, then partial derivative of ht with respect to parameters. And we can decompose it into the following sum here. We start with the derivative of the last ht. Then we say we have this another guy here. So we take a partial derivative of ht with respect to ht minus 1, and have ht minus 1 derivative with respect to w, and so on and on and on. And we can say that we decompose this guy into a product of these derivatives related to each ht. Okay, do you get the idea here? Why do we need this more complex structure, more complex backpropagation if you're talking about W? Let someone explain what's going on. Maybe let's start with Evgeny Khrushkov. Evgeny, can you explain to us what's going on the slide and what formulas we have here?
Yes. Okay. You mean these formulas in the
in the bottom? Why it's different from like when we try to calculate the derivatives with respect to u?
So this is back propagation respect to the weights of the model.
Yes, exactly. Okay.
And we take into account the weights of models t minus 1 and so on.
Yes, I would like to say yes, because each h depends on w, and so to calculate this full derivative with respect to w, we have to take into account all the stuff. Thank you, Evgeny, for your answer. So we say that, okay, calculation of these derivatives is kind of a more complex guy, and typically we just say that we want to have only parts of this guy, of this product, we have very long sequences, and we have this gradient clipping. We look only at part of the sequence, and this one of the explanation of why don't we have large memory, because we have this like gradients of vanishing if we have very long sequences. And okay, we have this first problem. Another problem is that we have sometimes very large gradients. Maybe we move in the wrong direction and so on. And this is an example of how we train some neural network, and we have this red loss function. And we can say, okay, sometimes we have very strange spikes here that are related to very large values of the gradients. And so we say, okay, basically we say that this gradients is like this. And we can try to select this threshold and say that we would normalize our gradient by this threshold. We'll normalize by the norm of this vector. And so we have this J with a wave to have an update. And we say, okay, our now W G plus 1. Okay. As a next epoch would be by K plus some alpha G. And the G is different, and we like limited the norm of this gradient. And now we have a more stable performance here. Also, when we have these big gradients, we can try to look at chunk of the data, so not look at this whole sequence when I do backpropagation, but stick to some part of the sequence and have it like this. But we have another problem here. As we see, we have a lot of products here. And if some of these products, if some term of this product are small, so something very close to 0, then all products is also close to 0, and our whole derivative is very close to 0. So product is close to 0. And so we have this gradient vanishing. Also, it's very hard to detect. So gradient vanishes. You see, okay, this loss function converges because we no longer have large changes because our gradient is small. So it's kind of hard to detect and very close when you look at the loss function dynamics to what you will observe when you are talking about the convergence of our approach. We can try to deal with this problem with some engineering tricks. The first trick is to use different activation function. Rectified linear unit typically works better than what we have with softmax and hyperbolic tangents. So when we are trying to produce Neuhina state, use hyperbolic tangents instead of, or ReLU instead of hyperbolic tangents to make better. Also, it makes sense to try to adjust initialization parameters to avoid situation when we have this vanishing gradients from the very beginning of the training. So typically bias is something initialized to 0, and weights is like identity metric, so we have non-zero gradients. Maybe you should have some noise here to get a better prediction. And so you can try to make a couple of runs to get something at the end. But in any case, it happens that this classic RNN architectures forget things very fast. Because, okay, they store a lot of information in this hidden information, in this hidden state. So we have a solution to deal with this problem. It's gated architectures. There are two most popular ones, a gated recurrent unit and long short-term memory. So let's look at them and why are they different and why do they have different behavior here. So basically we try to, okay, you can imagine of what's going on with this stuff. This is like, we have RNN here. We have some input ht-1, input x, hyperbolic tangents, and some output and some Neuhina state produced with this linear transformation. Okay, we can say for LSTM, the idea is to have a separate part related to short memory and a separate part related to long memory. Hidden state and cell state correspondingly. We will like dive into the formulas a bit deeper, but also we can try to simplify it in GRU that tries to also say what's keep, what's to forget, and identify what we want to keep and what we want to forget to make it's more stable. Let's start with historically first model, LCM. It's the same as RNN, but has a different structure inside here. It was invented quite a long time ago, but as people didn't have powerful machines back there, it wasn't universally acknowledged, and no one invented machine translation based on this architecture in the past. So what is like the components of this unit of this long-term, short-term memory machine? We say that we should have for cell state two parts. Part that is related to forgetting of information, and parts, okay, is multiply on how much we want to forget some part of this vector. And an update part related to what we want to add to the cell state information that keeps information in general. We also have a hidden state here to identify how much we should forget. And in this case, we look at hidden state. And say that this forgetting vector is a product of concatenation of hidden state and hash by some weights matrix W and some bias and also some linearity of top, for example, a sigmoid function. Also, we have another part, update part. To update part, you should say how much we should update and what we should add to this update. It's quite similar to what we have in RNN. So we say that this part is practically RNN, but with CT instead of HT here, but inside we have this hyperbolic tangents vector parameters, some bias. And here is the input, is a concatenation of H and X. And also we have this separate part. Another how much we update everything, also based on hidden state and X here. So basically we have this FT that signals on how much we forget here. So we multiply by the initial cell state to forget something. For you can imagine that some parts here are zeros, and we just completely drop this part of the cell state vector. And also we have this update part. We generate new information to include into the cell state, CT with a tilde, and IT also multiplier that tells us how much we want to keep. Apart from cell state, that's the most important information, we want to update everything else. So we update the output here, and we update the hidden state. Hidden state is like a simple function of the current cell state that is multiplied by additional parts, what we can say like an output, for example. We can say and so we have this detailed LSTM block completely defined, but like when you want some informal way to think about LSTM, we have separate cell state. It's like starts with forgetting at each time moment, then with updating, and we have a new cell state. And this cell state helps to control the hidden state, like this short-term memory hidden state. And in the process of doing all the stuff, we incorporate our new input. Yes, usually both cell states and hidden states are vectors here because we have matrix of parameters to produce like from one vector another vector. So we can say it's some valuable information, and definitely we can have more than one component in valuable information dealing with complex problems. Okay, another example of the more efficient units are gated recurrent unit. In this case, we also have update gate and slightly different reset gates. So let's look on what's going on. We have the separated part. So we have this X hash, and from X and H, we produce like a new FT. Also, we produce, okay, this is about what we forget here. And when we look here, we have this product component by component product of the previous hidden state and R, and we tell our neural network, our hidden state, what we want to forget. Also, we have the ZT on what we update here. And in the end, we produce this modified hidden state H till T. That is the product of what we have right now and what we should keep. And this is what we update. And also, this is what we keep from the previous state in the final formula for the final hidden state. So this is how GRU works. It works pretty fine in terms of how long memory it can maintain. And the idea is pretty much simple. So you should forget something, update something. Typically, GRU is slightly worse than LSTM. But if you look from the other point of view, it's much simpler, it trains faster, and if you don't have enough data, GRU can be your solution here. It's an interesting question. Can we construct a better block, a better recurrent block here? And so there are some answers to this question, and first one comes from the paper by given at ICML in 2015. So we can say, okay, this LSTM and GRU and all sounds like some very empirical stuff. It's kind of very strange that they were selected. Maybe we can learn something better. Also, we can try to identify what parts of LSTM is crucial and what parts are just here. So let's try to generate 10,000 architectures on some problems related to natural language processing and something different for sequential data. When we use some initial filtering, we have only 1,000 architectures. And also to make sure that we are not biasing something, we also try to select hyperparameters for each of these architectures to construct a better block. So we tested about 230,000 configurations here. And we say that if we try to get better, we say that we have these three guys. We stop performances. In this table, you can see the performance, and you can see that three problems we consider. And mute 1, mute 2, mute 3 is this new architectures we generate with genetic algorithm. And you can see that, okay, these new architectures, they're quite similar to GRU, but maybe a bit different. And so, for example, let's look at the best one among generated mute 1. Again, we generate some Z from X, we generate R from X and H, and we generate HT plus 1 by keeping it like this. So we have this is what we remember, this is what we keep, and this is what we forget. Basically, what we add, what we update here, and this is quite similar actually to GRU. We can compare these formulas to these formulas, and for some reason, maybe it was due to some not very big space architecture generated, but you can see that it's not an easy task to attack the problem when something different. Another problem, also by prominent scientists, and you can see that there is Schmidt-Huber in the authors. Again, we're trying to improve LSTM. we'll hope to use some 8 LSTM variants, and we are trying to improve not architecture, but improve the hyperparameter selection. And you can see that there is no much improvement compared to the initial variant, so LSTM is pretty much optimal. Also, another paper by my colleagues, Nikita Klyushnikov, Trofimov Ilya, Ekaterina Artemova, Mikhail Salnikov, Maxim Fedorov, and Evgeny Burnaev. Can we try to invent architecture using narrow architecture search? Can we try to invent a better LSTM block? Again, we have these simple rules inside the architecture, like linear part, blending element-wise, what we call like this forget and update parts, and also different activations, different element-wise operations. We limit the search space to avoid very large architectures that are kind of hard to train. And also we state that each architecture each architecture we know before, LSTM, GRU, and RNN belongs to this search space. So we are trying to generate better architectures and see how many parameters and how many training time we need. And also you can see that there is 3 common guys, RNN, LSTM, GRU here. Then they're like kind of in the middle. And when we are looking at the performance for this problem, it occurs that RNN is worse than typical architecture, but LSTM and GRU are pretty good. So in this way, we don't find better architectures for GRU and LSTM. And this is the end of the story for NLP, but for different types of the data, we can try to run something similar and obtain a better accuracy. So again, we have a lot of architectures. Each point here corresponds to an architecture. We compare different problems and different architectures here. And what you can see that we can do slightly better than the vanilla. In the left, actually, LSTM transformer and GRU provides better performance compared to this was the transactions dataset. GRU and transformer are better than the best architecture we found with our narrow architecture search. But if we try to improve GRU and select better parameters, then GRU happens to be even better. If you consider a different problem, so you want to predict gender based on transactions data, then we have slightly different situation. We see that there are some architectures that are better than the default ones, better than transformers, than GRU, and so on. But also we can see that hyperparameter selection is crucial. If we tune hyperparameters for GRU, we improve over all new architectures we invent. So what conclusion we can, okay, maybe we can drop this part and go to the one short notice that we can do multi-layer architecture, so we can have not only one LSTM RNN block, but also we can try to go back in bidirectional LSTM. In this case, we try to learn from the past, and in some problems it makes sense. For example, when we do handwriting recognition, speech recognition, and protein structure prediction in bioinformatics. And okay. Let's go to the conclusions. You can see that if you have more complex data, semi-structured data, then classic methods are not enough. They work worse because we need representations. We need to learn representations, and we need to meet these 4 design criteria on how should we treat complex structured time series data. In this case, we can switch to neural networks. They are flexible and then can handle almost any problems. They can solve one-to-sequence, sequence-to-one, sequence-to-sequence problems, and they kind of useful and provide top performance. Especially, like we can look at an example of machine translation problems, very good for testing neural networks They're definitely better than other types of models. The basic idea that leads us to this kind of results is recurrent neural network, like a single block that repeats itself during application of the model. And by processing data with recurrent neural network, we will have like a good representation and a good solution to many problems. We can try to improve this vanilla RNN block by introducing LSTM and Garou blocks. It's some heuristic adding of what we had before, but they help to maintain a long memory and provide a strong baseline. It's hard to beat. We can't come up with architecture that is better than LSTM and Garou for all problems, even if we define quite large search space. So we empirically found like the best configuration actually, and for hyperparameters and for architecture itself. And the basic idea is to learn to forget something, learn to fail, to remember something, and learn to update this model, to keep the essential information about the past and provide this information for the future prediction. So that's all for today, for the lecture. I will have a seminar in 5 minutes. And so good luck, good day, and good seminar. Goodbye.
Actually, I have one question. Am I?
Yes, you
you
can
hear
ask
me?
it.
So actually, we are working with vectors, right? At a particular
Yes.
time step.
Yes,
Is it possible to work with like matrices or something like that?
Okay, you can work with matrices as well as with everything else. There is no problem about it. So you can, for example, okay, maybe it's an important question, and thank you for it. And we can imagine something like this. For example, we have like video frames here, like at each time moment, like and on and on and on. And we can use some convolutional neural network here to produce some embedding. And we can use this embedding to deal with put into RNN block. But for sure, you can try to invent a better configuration and a better model in the end. Also, you should remember that we usually don't have this kind of vectors when we're dealing with text. But we again learn this embedding. It's very important to learn this embedding as well. And also, it's nice property that we can later use and reuse this kind of embeddings here. There are some architecture specific to video processing, but I suppose we will not cover much of them in the course because we don't have enough time, unfortunately.
Thank you.
You're welcome. Any other questions? Okay, thank you again. Goodbye.